In this video, I want to have a look at integration problems that involve inverse trig functions. So we've already had a look at differentiating. So integrating is obviously just going backwards. So if we're integrating this one, we end up with sine inverse. Integrating this gives us cos inverse, and integrating something that looks like this gives us our tan inverse. Now there's a few things you need to know. This first formula for sine inverse and this one for tan inverse, they are on your formula sheet. The one for cos is not on your formula sheet. The other thing we need to know is that this cos inverse, you'll notice when we're integrating, it's exactly the same as the one that gives us sine inverse, except for that negative. So this, as well as it being equal to cos inverse of x on a plus c, it could also be equivalent to minus sine inverse of x on a plus c. So both of those things are equivalent, so they're both correct. The other thing is this integral is written on your formula sheet in this way. But you'll often sometimes see it as well as a over a squared plus x squared dx is equal to tan inverse of x on a plus c. So rather than dividing by a over here, we've just got that a in the top. So sometimes you'll see it like that in a problem. All right, so let's have a look at some examples. So our first example asks us to integrate 1 over the square root of 25 minus x squared. So in here, our a would be 5 because 5 squared is equal to 25. Then if we have a look at the format of that, we know that it's going to give us sine inverse of x on 5 plus c. Our second example, if we have a look in that denominator, we can see that our a is going to be 2 because 2 squared is 4. Now because of that minus, we have two ways we could write this solution. We could write it as cos inverse of x on 2 plus c. X on 2 plus c, or we could write it as being equal to minus sine inverse of x on 2 plus c, and they're equivalent, so they're both correct. Our third example is the integral of 3 over 9 plus x squared. So in this case, our a is 3 because 3 squared is 9, and we also have that 3 in the numerator. So for this one, that's going to integrate to tan inverse of x on 3 plus c. So those three examples are sort of the most basic cases that you'll get because they're already in the form that we want them in, so we can just apply them straight into our formulas. Let's have a look at two examples that actually require a bit of manipulation to get it looking how we want it to look. Okay, so for this example, we're trying to find the integral of minus 1 over the square root of 1 minus 16x squared dx. So the problem at the moment is this 16 here. Every form that we have has that x squared having a coefficient of 1. So we're going to have to manipulate this so that it does have a coefficient of 1. So what we're going to do, off to the side here, I'm just going to write out what that denominator is. So 1 minus 16x squared. And I'm going to manipulate this and then put it back in. So if we want that x squared to have a coefficient of 1, I'm going to pull 16 out. So I'm going to factorize out 16, which would mean that this 1 will become a 1 over 16. And then I'll have my minus x squared that I was looking for. Now that's 16, we know that the square root of 16 is just 4. So that whole denominator can become 4 over 1 over 16, 4 root 1 over 16 minus x squared. And we also know that 1 over 16 can be written as 1/4 squared minus x squared. So that means that our a is going to be 1/4. All right, if we put that back in here, what that means is we're going to have minus 1 over 4 root 1/4 squared minus x squared dx. So I'm going to pull this 4 out the front, out of the way. So I'm going to have a quarter times the integral minus 1 over the square root of 1/4 squared minus x squared dx. When I integrate that, I'm still going to have my quarter. We know that this is going to integrate to cos inverse. Now it's going to be x over a, so that would be x over a quarter, but we know that dividing by a fraction is just the same as multiplying by the reciprocal. So x divided by a quarter is the same as 4x, and then I've got my plus c. Now if I'd pulled, instead of pulling a quarter out the front, if I'd pulled minus a quarter out, then we would have ended up with minus a quarter sine inverse of 4x plus c, and that's also correct. Our last example is a definite integral, so we're integrating between 2 and root 12. 1 on 4 plus x squared dx. So I'm going to rearrange this. Because there's no square root in the bottom, we know it's going to be tan. I'm going to make the numerator a 2, so that, because if we look at our 4, we know that a is equal to 2, because 2 squared is 4. So I'm going to make the numerator 2 as well to match, which means I'm going to have a half out the front to compensate for that. So I'm going to have 2 over 4 plus x squared dx. And then I can integrate. So I'm going to have a half outside of. That's going to give me tan inverse of x on 2. And that's going between root 12 and 2. If I substitute those in, I'm going to have a half outside of tan inverse of root 12 on 2 minus tan inverse of 2 on 2. Then I'm going to simplify these down. So I'm going to have a half outside of tan inverse. Root 12 can be split into a 4 and a 3. So that becomes a 2 root 3 over 2. But if we've got that over 2, that can just simplify to a root 3. And then I've got minus tan inverse of 1. Oops, that's an 11 of 1. All right, so then I'm going to have a half outside of tan inverse of root 3 is pi on 3. Tan inverse of 1 is pi on 4. And if I simplify that down, I'm going to end up with pi on 24. So that's having a look at integration that involves inverse trig functions.